my name is Olivier. I work at FCS, and today I'll be talking about the robust lock-free ring buffer protocol over shared memory, which Mathieu mentioned earlier. So, first of all, why doing IPC over shared memory instead of just doing a syscall in the kernel? That's the first question somebody could ask. So, well, first of all, the performance overhead of a syscall quite expensive, even today, even more with the mitigation. And at the time that Mathieu wrote LTTng, the first version with the ring buffer, there were no ABI for the kernel. And nowadays we do have user event, even though. So I did some benchmark just to show quickly. This is micro benchmark, so take this with a grain of salt. So user event plus ftrace to integer to the kernel, it's 9 nanoseconds per event, compared to the ring buffer of LTTng, which is 900, sorry, yes. And 90 for the LTTng ring buffer. So one order of magnitude difference. If we disable the mitigation for the kernel, we do have better overhead, but still, we're still in different ballpark. So this explains, even for today, why we're not using syscall for user space instrumentation. Just a quick overview. I know it's not very visible to everyone here. It's just that the ecosystem of LTTng, basically there's three components that you have to remember for this talk. You have the consumer daemon, which is a process that consumes the events and write it to disk. You have the session daemon, which handles session. And you have, well, the user application, basically. Other components are not very of interest here. So the history of the shared memory ring buffer in LTTng. So in version 2.0, we only have per process ring buffer. So every time you launch an application that you want to trace, a ring buffer was allocated for that application and was used by that application. So there was no sharing of this ring buffer with other processes from the user or on the systems. And of course, the consumer daemon had access to, which is why it was in shared memory. But when the process died, well, this ring buffer was simply reclaimed and everything was fine. In 2.3, we introduced the per user ring buffer, and it's been the default since. So instead of allocating this for every process, we allocate a ring buffer for the user, and this can be reused across processes. And this has many advantages that the memory is lazily allocated on first trace application start. The application start is now faster because it's, well, the first application that is getting traced will do the pre-allocation, and then the second one, well, the allocation is already there, so application starts much faster that way. And, well, of course, the tracing session memory use is reduced because now you compact everything under the user session instead of the per process. But then you have the problem as well, when a process dies during a transaction, and I will define what is a transaction, but basically when you're writing to a shared memory, what happens if you hang at a position where you were trying to write, you have state when you do a IPC over shared memory. And well, in the case, at that version, basically what happened is that the consumer daemon could not pass the hang position. So in a ring buffer, you have a produce position and you have a consumer position. And if the producer position basically died during the process of writing an event, well, the consumer position could not pass that position. And so every event past that position are basically lost. They can still be written to this ring buffer, but they're not getting consumed. And if producer wrap around the ring buffer, well, every event are discarded by default. So nothing is getting written anymore to the ring buffer even when you wrap around. So in 2.10, there was the introduction of session rotation. And basically what it does is that the consumer daemon, when it does a session rotation, it waits for producer to enter quiescent state, and I'll define that later. You can see the session rotation as a point of view of the user. You can see it as a log rotation on disk. Okay, this is like the basic view. But under the hood, it's very much complex because we still need to guarantee the lock freedom of the transaction for the producers. But then, since that version, destroying a session now basically imply a session rotation as one of the final steps to gather the rest of the events before closing up their session. And if a producer died during that transaction, now the session cannot be destroyed. Because if you remember, the consumer cannot pass the hang position, And if the destroy implies session rotation and the session rotation never finish, well, your session cannot be destroyed. And so from the point of view of the user, when you try to destroy your session, you basically see a lot of dots on the terminal just indefinitely getting print. And even though it's not hanging behind the scenes, just waiting for the producer to finish, but the producer is just not there anymore. And well, the consequence of that is that you don't have a full trace available. Like the last rotation is not available. So any event that are part of that rotation are not on the disk. And any resource associated with the session are not reclaimed by the session daemon. And basically, user have to restart the session daemon to get rid of that session. So this is a quick reminder from the last event that we had 2 years ago. Some nice properties that the user space tracer should have. The first one is integrity, the second one is reliability of result, and the third one is adaptability of the tracer. And in our case, we have a lack of reliability in that the results are missing. Some events are missing from the session rotation when destroying the session. And so the user kind of doubt the result that it gets from the tracer. We also have a lack of adaptability. We cannot adapt to process that crash during the transaction. And we have to put burden on the user because the user now has to restart its session daemon or other things like that. So the problematic, the original ring buffer transaction protocol, it relies on quiescent state. So we will just define a quiescent state to be any state that's outside a transaction. Now, I need to define what's a transaction. So you enter a transaction when you do a transaction for the reservation on the ring buffer. So basically, you reserve, you write, and then you commit. And that last step is a transition where you go outside the transactions. And so anything between the reserve and the commit, you can see it as not quiescence and outside quiescence. In reality, there's many more state, of course, than just those three. This is a simplified view. For example, when you need to deliver to consumer daemon, or when you at sub-buffer boundary, these are special cases that need to be handled in different ways, so there's many more state in these cases. So I'll give you a first scenario that can happen. For example, you're trying to debug a trace program. And so this is a multi-thread program. For example, you're putting a breakpoint in a function that's not even trace. But since the debugger is going to stop every thread, one of your threads could be in the process of doing a transaction, so it's not quiescent state. And now you're debugging and you would like to flush the trace to get the result. But then you see that your session daemon is, well, the comment for destroying that session is not finishing because, well, you have one of your thread that's still doing the transactions. That is because the commit is not done, and so you're in a quiescent state. And now what could happen also is that all other producer, remember, if you have per user ring buffers, you could have not only this process that you're debugging, you could have other processes that are running to the same ring buffer. Well, these will eventually discard the event once they wrap around the ring buffer. And yeah, our session rotation will wait for the program to reach its quiet stance. So basically, you cannot get the trace, and everyone will discard the event at the end. Another problematic scenario that you could encounter is that, well, for example, you could do a signal between your processes as an IPC mechanism. And maybe you want to stop an application that's getting trace with that signal. And if you receive that signal while you're doing a transaction, well, it's kind of like the breakpoint situation, but now you cannot recover from it because your application won't start ever again. You're stuck in that state indefinitely. And so all of the previous downsides are still there, but your session rotation will not be destroyed ever, as opposed to the GDB situation where you could just resume the program and then the destroy will finish. So these are like the main scenario, but other scenario are possible is that the producer can be hanged for reasons for debugging, and it could be hanged because it crashed. So one could ask, why fixing it 12 years later? So, well, there's a low probability of reselling a signal during a transaction. That it's a very short regions. Typically, when you're in the fast path, it's a very short region. But in some cases, it's more large. And it heavily depends on your program design. Like if you don't do IPC over signal, you basically don't have necessarily this problem. But it could be like, for example, you do a p kill by accident and you kill one of your trace application, and then you never get the trace because of that. Well, the hand of the trace, sorry, the last rotation. Also depend heavily on the system load, of course. So it is like many variables there. And we did add some report by the user over the years. And our recommendation first was to use the per process ring buffer instead. Like you don't have this problem with per process ring buffers, but you do lose the advantage of the per user that I've mentioned earlier. And also it requires significant engineering effort. We have to add new state to the ring buffer. It's a complex beast, and we needed a sponsor for that. So now I'll present the solution that we came with. The new transaction protocol now add new state transition to the transaction. So this is, again, a simplified model where basically before the reserve and after the commit, we take and we release an ownership. And you should not see that as a mutex. It's still lock-free. It's not something that, I know that ownership is maybe not a good term here, but basically this modification to the transaction protocol has 18 possible states, and I'll get to that later. We've made it that every of these states can be derived from internal free running counters of the ring buffers. So if an application crash, we can determine in what state it was based on some counters internal to the ring buffers. And this allows the consumer daemon to either complete or abort the stalled transactions. And it has a nice property that is still lock-free for the producer. And yeah, so just to mention that the ownership model, it's basically an ownership by subbuffers. It's not global to the ring buffer itself. So the ring buffer has many subbuffers inside of it, and every subbuffer has a owner. And basically the ownership is only based on that subbuffers. And whenever a producer wants to take an ownership that's already busy, it's skipped to the next subbuffer. So this keeps the lock free for the transactions. And so we did some reproducible fuzzy testing for that. So I mentioned that we have 18 states and we have an unbound number of producers. And so technically you could have n to the power of p scenario to test. You know, every of these producer could be in state. So infinite scenario if you scale to infinity, of course. So for entropic reasons, we only test at most at p equal to 3. More than that, it will yield more than 100k scenario to test. But how do you test that many amount of tests of scenario? So you need to crash the producer in the wanted states. So you have to select states and you have to say this producer needs to be at that state and that producer to that state, and then you crash them. And so we introduce what we call test point labels, which are basically just labels in a debug symbols tables, where you can, we've put it at strategic location where we have observable side effect. So a compare change on a counters, for example, is observable to other producer and to the consumer. And so this is like a state transition, and we mark it as a label there. So this is a test point. And then we need it to be reproducible. We don't want like to run many core on the CI, and we want like to try to get the state we want. And so what we did is that we have a deterministic scheduling of the producer state transition using the test point, but using GDB. So we use GDB to spawn producers, and we put breakpoint to say this producer will stop at that test point, and this one there. And then we see what happens. We crash all of the producer, and we see can the consumer demand can finish the transaction for us, and will we get a trace on the disk at the end that's not corrupted. And with this new protocol, I did the same benchmark, so that what was on my computer. And we can see that we add a 2 nanoseconds overhead by events with this new robust protocol. And there's some possible improvement in the future that we think of. Sorry. We could optimize some memory barrier in the fast path using the new memory model introduced in our user space RCU. Basically, now we are using a memory model that's much closer to the C11 memory model instead of the kernel memory model. And so we have
the old kernel memory model.
Oh, sorry, yeah.
Now it doesn't.
Yeah. So we are more close to a store release semantic bound to atomic operation instead of like having a memory barrier that's not integrated with the atomic operations. And we have also some plan maybe to use reproducible sequence. So the whole protocol, we've made sure that it was possible to implement it without any atomic operation, but only using reproducible sequence. And in conclusion, well, this feature will be available in 2.15 this year's. And now program that crash during ring buffer transaction for per user ring buffer for per process, this is not useful. Well, the session rotation will not hang. The session destruction will not hang also. And future event emission to the trace will not be prevent, basically. And this is made, by the way, in a way that a timer is periodically in the consumer daemon trigger, and the consumer daemon will go check the ring buffer and see if there's some owner that are dead. We have like a whole mechanism with ID that's generated in the session daemons that's passed to the user application, and these ID are reclaimed, garbage collected, and everything. Well, not garbage collect, but they're recycled. And basically, the consumer daemon can know when application have crashed, and they can scan the ring buffer to determine, okay, yeah, I know this subbuffer it probably hang. I'll make sure it's not. For example, it could see that a subbuffer is hang, but it's a owner that is not dead, so it's probably debugged or something like that, or it's very slow, so it's not going to emit a warning. But if it's know that it's dead, it's going to go to fix up for that process. And so it will ensure that the ring buffer is still robust, kind of like the robust mutex, right? Like if you auto lock with robust mutex and your application crash, I think that the runtime will make sure that that mutex is like unlocked, so you can relock it later. Yeah, and this feature add an additional 2 nanoseconds even on micro benchmark, but as mentioned, we have plans to fix that, well, to improve that. And overall, I think that the LTTng ecosystem is now more robust in general with that feature. And reference for the image and question, and yeah, that's it. Thank you.